Hello and welcome to my tutorials on data science and Python hand in hand. So this is the first of the lectures or first of the tutorials, and let's see what's new in this tutorial. So what's new? Let's see. Okay. So actually in this tutorial, I will go through the very basics I'll start with the very basics of data science or machine learning, and will try to give an intuitive understanding through programming in Python. So the course will be simple, easy to learn, and it will also give you insights into the intuitive understanding of how the algorithms work with Python programming rather than visiting the Python library. So eventually we will also visit the Python library, but if we can do the stuff with our own hands using the raw Python library, then maybe we get a better intuitive understanding. And this will also help us to learn Python if we are beginners in Python. So with every tutorial, I'll model it into two parts. The first part will have some data science theoretical part, and the second part we will have an intuitive understanding of that theory through Python programming. Okay. So that brings us to lecture one. The first lecture, we will cover very basics or prerequisites for data science or machine learning. So here are the main topics, which are the basic statistical concepts which related to mean, standard deviation, covariance, correlation, similarity, distance, dot product, and normalization. I'll try to make this interesting in the first lecture, though the main magic or the main interesting things start from the following lectures. So as I said, each of my lecture will have two parts. The first part will be the theory related to data science, and the second part will be related to Python. So what we will do in the theory in the practical of this lecture is we will start from the very basics of Python, and we will start with the installation of Python, or I'll guide you through the installation of Python, and I'll go through some basic concepts of Python like modules, packages, and classes. And then we will see the different options we have of executing Python quickly. Uh, and then comes the main interesting part where we will implement the basic concepts of statistics through Python. Though Python itself has a library for each of these statistical concepts, but we will try to implement it from as core as possible, so that it serves our second purpose of learning Python. Okay, and this will make you ready and confident with Python as well towards the end of the course. Okay, and finally we will, after executing these programs, we will try to package this into a Python module. Okay, and I'll try to give something so that you can try yourself and test your skills. Okay, so let's get started. Okay, the first thing is very simple. The very basics steps of statistics is mean, and along with it, I'll also go through standard deviation. Okay, so mean, as we know, is actually an average. So we have a group of soldiers here, and we have their heights, average heights. You can see these are the heights, average height of each of the soldiers. So what is the mean? Mean is nothing but the average. So we have the sum of all the soldiers and divided by the number of soldiers. That is sum of their heights. So that is the mean. And there's an alternative way also, like we can see there are repetitions of values. So if you only have the distinct values and their corresponding frequencies, so you can take the second formula as well, like the distinct data into frequency and divided by the number of frequencies. And you will find out that the mean comes to 65.29. But what makes mean interesting? Let's see. So here I have sorted out the heights and their corresponding frequency. And if you see, if you this is the statistically we represent through this formula on the mean. And if you see, if we represent this through a graph, the graph turns out to be like this. That is, if we plot the frequencies of each of the heights, the graph usually turns out like this, which is very similar to a normal distribution. And you will see that if this follows a normal distribution, it means that majority of the data are centered around the mean. So the highest frequency or the highest occurrences of the height of these soldiers around the mean, which is 65.29. Okay. So you need the takeaway from this slide is you need to remember that this is how the mean in a mean looks in a normal distribution. So now we will take it forward and understand what is standard deviation. So you remember the graph, the plot we saw on our last slide. So this is the mean, and here are small arrows. So actually, in a normal distribution, this is the standard deviation, or it's the measure of how much the data varies from the mean, or how much variance is there in the data. So usually, if we smoothen, let's see if we can smoothen this curve. If we had a huge curve, we did not have too many data. If we had a lot of data and they followed a normal distribution, the curve would actually look like this. And this center line shows the mean, and this is the standard deviation. So it gives the shape of this. Both mean and standard deviation helps to define the shape of the curve in a normal distribution. Okay, and this and the mathematical formula for standard deviation is this. So mu here is the mean. So from each data, you can subtract the mean and take the square, and then sum over them and divide it by the number of observations. And variance is actually the square of this standard deviation. So the data we saw on the previous slide has a standard deviation of 4.11, which means this width is somewhere around this value. And this measure gives us how much the data varies away from the mean. Okay. So now we have a new intuitive understanding of what is mean and standard deviation. Okay. And we might need to refer to these definitions in future also. So let's move forward and let's learn two more important statistical measures. They are covariance and correlation. Okay. So there's a reason I have written them down on the same slide. So this is the formula of covariance. You can see it's actually what was standard deviation. Standard deviation was the measure of how much a data varies, how much a data actually varies, how much spread the data is. And covariance is the measure if we have two sets of data, like one may be measuring the height and one may be measuring the weight, or one may be measuring the height and one may be age, how much these two data vary together. So that is the definition of covariance. So we have two sets of data, one is x and one is y, and mu x and mu y are the mean of these two data, and by this formula we can calculate how much both the data vary together. Similarly, what is correlation? Again, correlation is also related to two sets of data. We can find whether both the data are correlated or not. It's close to covariance. There's a relation with covariance also, but it actually measures whether increase or decrease of one of the values influences the increase or decrease of another value. So maybe whether, for example, we can inference whether a height varies along with the age or not. So with an example, things might become a bit clear. So we can see on the left hand side we have the age and weight of certain children between the age of 5 and 10. Okay, and on the right hand side we have the age of some adults between the age of 30 it ranges from say 20 to around 35. Okay, now let's see what is the covariance of both. In the left hand data you can see that the correlation of the data is 0.97. That is for the children, that is for children between ages 5 and 10, the weight is very much correlated to the age. That is, the weight increases with the age. Okay. So the more and more the correlation is equal to my 1 plus 1 or minus 1, we can say that there is a relation. And more it's towards 0, we say that it doesn't. Both the both the data are independent of each other. And you can see the covariance is 9.71. That is, both the data also vary together a lot. Okay. On the right hand side, you can see that the correlation of adults with age and weight is almost very low, 0.29, and it has it is also found that the correlation is negative. So apparently, from the ages between 20 to 35, there's no correlation of age and weight. Okay? And similarly, the covariance is also very less. Okay? And if you observe very carefully between the formulas in this page and the last page, you would find out that the correlation is nothing but the covariance divided by the standard deviations of the both the variables x and y. Okay. And why we are having n minus 1 here, also we use the same, we don't use n in standard deviation calculation because we do not have the population data. We always give some sort of sample data. For sample data we always divide by n minus 1, which is the degree of freedom. Okay. And these are some takeaway points. A correlation can vary from -1 to +1. If it's close to +1 or -1, it's highly correlated, otherwise not. Okay, and correlation of a variable with itself always 1. Okay. Next comes distance. So this is a very important concept in data science, and I'll try to explain it in simple terms. Okay. So let's say we have the data of age and salary of employees of a particular company. So age is 21 and salary is 30,000. Age is 22 and salary is 40,000. We can see that. Now we have only two variables and we could easily plot them on a two-dimensional graph. So let's plot. So along the y-axis we have plotted the salary, and along the x-axis we have plotted the age. So what do we see? So if we had to find two persons, so each of the dots here is represents a person, and we can, from these dots we can find out that this person has a salary around 70,000 and age is around 22. So in data science we will frequently represent each individual or each object in a two-dimensional or a higher dimensional space based on the number of features. Like for example, in this one we have only two features, and we can present each of the individuals. Each row represents an individual, and each individual can be represented as a plot in a two-dimensional graph. So if we had more features, we would require a higher dimensional graph, and if it goes beyond 3 dimensions, it's a little difficult to intuitively understand that. Now we can see that among all these two data are very close to each other in the graph. So for 2 dimension, we could easily find out that these two are very close. Okay, so this is the distance between these 2 points. So between these two individuals, we have a way of calculating the distance. So let this point, if we consider this point as P1 Q1 and the second point as P2 Q2, then this is the formula of the distance. dpq square root of it's a mistake. It should be P1 minus P2 and Q2 minus this needs a correction. It's P1 minus P2 whole square minus plus Q1 minus Q2 whole square. Okay, so this is how we find out the distance. So these are the 2 points I have magnified, and its coordinates are P1 Q1 and P2 Q2, and so the points will be P2 minus P1, and this distance will be Q2 minus Q1 minus Q2, and easily we can find this out using Pythagorean theorem. This is the distance. But how do we find this distance? I mentioned that we won't be working with only two features, right, of an object or an individual in this case. We can have more features, like we can have age, salary, weight, height, etc. And this formula is quite intuitive. So distance between 2 points P and Q, and if P's coordinates are P1, P2, Pi, Pn in an n-dimensional space, and Q's coordinates are Q1, Q2, Qi, Qn in the same n-dimensional space, then this is the formula of calculating the distance between two data points. And each data point, as I mentioned, represents an individual or the data set that we are interested about. So there's another measure called cosine similarity, which helps us to measure the similarity or the distance between two objects. So I'll come to the difference of cosine similarity with the distance. The distance we saw in the last slide was actually Euclidean distance. So cosine similarity measures the angle of the vector of these 2 points. So you can see each point is represented by a line starting from the origin to that point, which is the vector for that point. And you can see on the right hand side, theta is the angle between two of the vectors. So this also helps us to measure how much similar two data points are. As you know, cos theta is 1. So if cos 0 is actually 1. So if they are almost identical, this angle would turn out to be 0. So there's a formula to measure this angle, which is if two points are vectors A and B, we could measure them by A dot B, which is summation of AI bi, by the norms of A and B. Let's see an example in the next page to have a clear understanding of this. So dot product and norm, we'll go into details. Again, we have these 2 points A and B, and A coordinates are 22, 35,000, and B's coordinates are 21 and 30,000. That you can easily find out from this graph, and we also have that data. So what is the dot product? Dot product is the sum of the corresponding products. 22 into 21 plus 35,000 into 30,000. So this is the dot product. And what is the norm? Norm is actually the length of the vector, and the formula is square root of the norm of A is square root of 22 square plus 35,000 square, and the norm of P is square root of 21 square plus 30,000 square. And you can see the values are this 35,000.01 and 30,000.01. So this is and then we can find the cos of the angle between them, and it turns out that if we do A dot B divided by the norms of A and B product, is 0.99, which is also very close to 1, and which means these points are very similar. Okay, and intuitively you can expand the formula of both dot product and norm for higher dimensions. So since there are 2 dimensions, we are taking square of both the coordinates and then the square root. If it was in dimension, it would look like this. And for dot product also, you can multiply the corresponding points in each of the dimensions and sum them up. Okay. Okay. The next concept is normalization. So this is a very useful concept. So let's look at the data of age and salary once again. So if you remember, then we took these 2 data, right? And sorry, the one that was having something else. Okay, it was, I wrote it as 35,000 in let's call it, doesn't change anything though. So if we look at on our previous slide also, we can see that the data for the salary varies in the range of 35,000, 30,000, and some above 10,000 something, while the data in this of the age is just 2 in 20s or 30s. It's a huge difference, and so the norm is highly overpowered by the dimension, by this actual the salary. Okay, so somehow here we are not if we do any further calculation, we are not giving much importance to this age. So a basic practice in statistics is first to scale them so that both of them can be in the same range. Okay, so how do we do that? Yeah, here is the calculation again. It shouldn't be 35. I think it was something around 40,000. Maybe we can, or 30,000. We can correct it later. But you get the idea. So here we have two forms of scaling the document. So each of the rows we can scale with either. There are many scaling techniques. I am explaining two. So min max scaler. Each of the values here we scale using the mean of that. We subtract the mean of these values and divide it by the range of these values. So mean of these values you can see is 19. So 21 minus 19, and the range of these values is the max minus mean. So here we have the max as 30 and the mean as 19. So 11. So to normalize this value, after normalization, it would come as 2 by 11. So similarly, we do for all the data here, and we can do the same for salary. And a more popularly used technique is standard scaler. For each data, we subtract the mean and divide it by the standard deviation. Okay, so see here after doing this standard scaling, both the data are in the same range, both the columns. Okay, so this is an useful technique of before working on any data. So this brings to our end of the theory of lecture 1 almost. Apart from that, I mentioned there's one more relation between correlation and covariance, which I did not extend at that time. Here you can see, you can do the calculation, you can try out the calculation and put me and let me know. So here you can see correlation of two variables is actually the covariance of their standard scaled values. Okay? So that's a bit of calculation you can do on the formula. So that brings us to the end of lecture 1. So this is just we learned some statistical properties of data which will be required as a base for the algorithms that we learned in the lecture. And from here we will move on to our practical, which is getting started with Python. Python is the